Let's go with
All
the
right.
first speaker.
Our first presenter is Mojtaba Parsaee, and Mojtaba is coming to us as a postdoctoral scholar and lecturer at Laval University in Quebec City, and his expertise spans sustainability and healthy built environments with a focus on biophilia and bioclimatic design, in particular in cold and extreme climates, which I think is important and exciting because especially of the decreased solar exposure. So his presentation will be on photobiological impacts of Arctic daylighting and seasonal photoperiods on designing daylit spaces. Welcome, Mojtaba.
Yeah, hi everyone, and good morning from Quebec, Canada. Thank you for the introduction, and thank you, VELUX, for inviting me. My presentation is about the photobiological impacts of Arctic daylighting and seasonal photoperiods on designing buildings in northern Canada. Since my doctoral research, I've been studying Arctic climatic conditions, building models, and their lighting design system, and people's needs and wellness in northern Canada. And my research is funded by the Sentinel North project at Laval University, which is aimed at training interdisciplinary researchers to develop our knowledge about the Arctic climate and its impact on people's health. So in this presentation, I'm going to talk about photobiological lighting doses that Arctic climates offer to people and how existing buildings in northern Canada deliver such photobiological doses to people. The main focus of my presentation is on providing proper daylighting qualities, especially in terms of color temperatures and darkness, at the proper time of the day to people in the Arctic region. That refers to above 60 degrees northern latitudes. That is interesting as occupants of this region experience very different daylighting features and day-night cycles compared to those who live in southern and mid-latitudes below 45 degrees. So a general perspective about Arctic daylighting is that people are exposed to strong variations in photoperiods and day-night cycles throughout the year. Like this example showing photoperiods in Cambridge Bay, northern Canada. I put hours as the horizontal axis and months as the vertical axis. So you can see in the summer, people could experience long days or polar days with midnight sun phenomena and almost no darkness. And then in the winter, Arctic occupants have a few hours of daylighting or almost no daylighting in some months. The sun comes in very low altitude angles most of the year. The sky is mostly cloudy and overcast, and the ground is covered with the snow for several months of the year. And the combination of these features creates hourly and seasonal daylighting qualities available to Arctic people, which could cause or worsen photobiological problems. And so far, many studies have shown photobiological disorders in Arctic and Antarctic regions, including desynchronized circadian rhythms, sleep problems, depressions, and daytime confusions. I'm not going to talk about them, but the important point is that these photobiological disorders are reported during Arctic summers and winters, and in both indigenous and non-indigenous communities. It is also shown that such problems are related to climatic conditions and natural lighting, as well as artificial lighting inside buildings. So this is an important difference between the Arctic and mid-latitude climates, as daylighting outside buildings could not always positively improve people's health. So an intriguing question is that what photobiological daylighting doses do Arctic climates offer to people? And what are the differences between the available photobiological doses in the Arctic and mid-latitude climates? And to answer this question, we've looked at the general recommendation for healthy lighting design of buildings, which is said to provide people with proper lighting qualities at the proper time of the day in relation to biological and social times. And to be more specific, is recommended to provide people with cool, bright lighting in the morning and early daytime, followed by warm and dim lighting in the evening, especially a couple of hours before going to sleep. And finally, provide the occupants with darkness during the night and sleep times. So recommendations emphasize on the exposure to a stable and regular daily light dark cycles, which is likely to reinforce good alignment of circadian rhythms and further benefit sleep, cognitive performance, and health. And some metrics and thresholds are also developed, including melanopic equivalent, daylighting, illuminance, and circadian stimulus, which I think you already know about them. The key features of these recommendations are the color and intensity of lighting and timing and duration of the exposure. Based on this, the hourly photobiological lighting dose defines the color and intensity of lighting which could address photobiological needs of a person. And a photobiological lighting adaptation scenario defines how lighting features should be changed during a day to deliver proper photobiological doses at the proper time of the day to occupants. An important issue here is that recommendations are mainly developed in relation to artificial lighting and indoor lighting conditions by considering that natural lighting outside buildings could generally provide people with sufficient and appropriate lighting qualities and darkness at the proper time. But Arctic daylighting, the Arctic daylighting conditions do not offer regular lighting qualities, especially in terms of color temperatures and darkness over the year. Here, you can see some of our in-situ measurements of daylighting in Cambridge Bay, northern Canada, which are captured by my colleague Tarlan Abazari. Tarlan captured several 360-degree high dynamic range images. We then calibrated and post-processed the HDR images, especially in terms of color channels, to visualize lighting, sky, and ground conditions, which a person can see in the entire field of view. Here, you see some examples which show Arctic occupants are exposed to very cool daylighting, more than 6,000 or 10,000 Kelvin throughout the day. We also rendered the ratio of melanopic to photopic units for the capture scene. As you see, intensities of melanopic units are higher than photopic units during the day, which potentially means more impacts on circadian rhythms. We received such photobiological doses under almost clear sky conditions with direct sunlight. When the sky is overcast, which is the case for most of the time, especially during Arctic summers, we have more extreme conditions in terms of higher color temperatures and higher melanopic units throughout the day. Another issue is that overcast skies are usually related to more negative emotions and feelings. The in-situ measurements further intrigued us to simulate photobiological doses that we could get in northern climates for the entire year to better understand the lighting exposure history of people. We tried to simulate hourly spectra of Arctic daylighting to determine photobiological doses. As a pilot study, we considered 36 different scenarios of sun, sky, and ground conditions to produce hourly spectral distributions of Arctic daylighting, which are then used to calculate color temperatures, melanopic and photopic units, and the ratio of melanopic to photopic units for the case of Cambridge Bay. Some of the results are shown in this figure. You can see how photobiological doses, especially color temperatures of daylighting, change from the morning to evening. To give you a better perspective, we also rendered photobiological doses for a mid-latitude city of Phoenix in Arizona, US, which is located around 33 degrees. Now you can realize that people in the Arctic are mainly exposed to cool daylighting from the morning to evening throughout the year, including the polar days and midnights of the summer. Such parameters in photobiological doses, such patterns in photobiological doses of Arctic daylighting are not generally aligned with the photobiological biological cycle of people. Where in Phoenix, people are exposed to an almost stable pattern of receiving cool lighting in the morning and warm lighting during the evening, then darkness at night. And this pattern is almost similar to the biological cycle of humans. Now, how do Arctic buildings in northern Canada respond to such daylighting conditions and people's needs? Well, they are generally not designed to address these issues. Here are some examples of our in-situ measurements in a recently built research center in Cambridge Bay. You can see that occupants are mostly exposed to a warm indoor lighting ambience, while the outdoor climate at the same time offers a very cool daylighting. This warm indoor lighting ambience remains almost constant throughout the day. And it's interesting that the vestibule of this building offers almost in-between lighting conditions, which are almost neutral. And such static lighting conditions without any variations in response to outdoors and people's needs are the main features of buildings in northern Canada. And in addition to these issues, buildings are not also designed to, in terms of visual comfort, visual discomfort and glare problems. Like these examples, occupants try to avoid the daylighting penetration by using thick wood panels or very conventional blinds that we use here in mid-latitude. I think it's obvious that these are not good strategies for such climates, especially the thick wood panels, which permanently close the windows and limit people's access to outdoor and daylighting. So I would like to conclude this presentation by outlining some major aspects which we are working on it in our research group to develop buildings and lighting design for Arctic people and climates. First, we need to focus on the spectral composition and color temperatures of daylighting and its dynamic behaviors, especially for northern and Arctic latitudes. Having the information of such daylighting features for the entire typical meteorological year could provide designers and biologists with a better understanding of available photobiological doses and lighting exposure history of people, especially in the extreme Arctic climate. And we have a plan to produce a database of HDR all-sky images captured in northern and southern Canada and the US in collaboration with Professor Melika Inanachi at Washington University. Our plan is to share the database with the public as an open science to enable everyone to use it and develop proper tools and solutions. Another issue is that we need further studies to recommend proper patterns for the exposure to Arctic daylighting conditions. And finally, we are working on adapting the architectural design of Arctic buildings, including lighting patterns to local conditions and hourly photobiological needs of people. We focus on the integrated design of windows, shading systems, surface colors, as well as artificial lighting to address photobiological needs of Arctic climates. So far, we've studied the impacts of shading systems on adapting photobiological parameters in such climates, which you can read about them in our publication. But overall, we still need further studies, especially experimental and interdisciplinary research to develop an integrated lighting systems for Arctic buildings. And I appreciate the opportunity to share some of our studies and thoughts with you today. And feel free to contact us for further information or collaboration. And if you have any questions, and thank you very much for your attention.